In this video, we will talk about confidence intervals. After watching the video, you should be able to explain why it is necessary to include a margin of error when we use a sample statistic to estimate a population parameter. You should be able to determine which confidence interval formula is appropriate to use in a given situation. Explain how sample size and confidence level impact the width of a confidence interval. Interpret our output related to confidence intervals. Write a sentence interpreting a confidence interval. Explain the relationship between confidence intervals and hypothesis tests and determine from a confidence interval whether or not a null hypothesis would be rejected. And determine whether it is appropriate to use normal or t-distributions to construct confidence intervals. Let's recall our survey we've been talking about pertaining to people's attitudes towards self-driving cars. The poll by Gallup found that 758 out of 3,297 U.S. adults, approximately 23%, said that they would be comfortable riding in a self-driving car on a regular basis. Based on this survey, we can believe that the proportion of all U.S. adults who are comfortable riding in these cars is probably pretty close to 23%, but we shouldn't say that it's exactly 23% because this was based on only a sample of adults. It's likely that if we went and took a different sample of 3,297 people, we would get a slightly different result. The question is, how close should we expect the true proportion of all U.S. adults to lie to the 23% that we saw in our sample? In the last line of the article, Gallup says, for results based on the total sample of 3,297 U.S. adults, the margin of sampling error is plus or minus 2 percentage points at the 95% confidence level. What does that statement mean, and where does the plus or minus 2 percentage points come from? That's what we'll explore in this video. Because our data were collected through a sample, we can use this sample to draw conclusions about the larger population of all U.S. adults, assuming we're confident that the sample was selected randomly in a way that is reflective of the larger population. However, because each sample was chosen randomly, results will vary from sample to sample. We don't expect the results we see in our sample to match exactly the proportions we would see in the true population. Instead, we use sample statistics such as p-hat or x-bar, the sample proportion or sample mean, to draw conclusions about the parameters that we're interested in, pi or mu, the overall population proportion or population mean. Although we can't say exactly what the values of pi or mu are based on our sample, we can determine whether or not a particular value is plausible, as we've been doing in hypothesis testing, or find a range of plausible values, as we'll do with confidence intervals. Let's recall a picture that we've seen before. When we worked with proportional data, we said that as long as our sample includes at least 10 successes and 10 failures, it's reasonable to approximate the sampling distribution for p-hat, our sample proportion, using a normal bell curve. In a normal distribution, approximately 95% of all samples will produce a sample proportion p-hat that lies within 2 standard errors of the true parameter value pi. The standard error is the estimate of the standard deviation for the distribution of p-hat, and it's given by a formula that we've seen before. It's the square root of p-hat times 1 minus p-hat over n, the sample size. Because we know that 95% of the area under this curve lies within 2 standard deviations of the mean, we can create a 95% confidence interval for pi using the formula p-hat plus or minus 2 times that standard error, square root of p-hat times 1 minus p-hat over n. In the self-driving cars example, p hat is 0.23 and n is 53, so plugging into that formula gives the result you see. When we perform the calculation, the lower number comes out to be 0.125 and the upper number 0.245. We could also use R to calculate this confidence interval using the prop test command, which we've seen before. And when we do this, underneath the information about the hypothesis test, it gives us a 95% confidence interval, which matches what we saw on the previous screen. Therefore, we can say that we are 95% confident that the proportion of all U.S. adults who would be comfortable riding in a self-driving car is between 0.215 and 0.245, between 21.5% and 24.5%. Notice that 25% is not in the interval, which makes sense because we previously did a hypothesis test for whether it was plausible for pi to be equal to 0.25, and we obtained a very small p-value and rejected that null hypothesis. In fact, there's a correspondence between confidence intervals and hypothesis tests. If we have a 95% confidence interval that does not contain a certain value such as 0.25, then when we do a hypothesis test for pi equal to that value, we'll obtain a p-value less than 0.05 and reject that null hypothesis. Now let's consider the Florida Lakes example. This is an example of a quantitative or numeric variable as opposed to a categorical one. We can make confidence intervals for mu, the mean mercury concentration in all Florida lakes, in this situation as well. We do it by using the t-distribution and its associated standard error for the sample mean, x bar. A 95% confidence interval for mu in this situation is given by x bar plus or minus 2 times s over the square root of n. This is valid as long as the conditions which we've previously seen still hold. That is, our distribution for x bar can be assumed to be roughly symmetric, roughly normal. That will happen as long as the data in our sample are roughly symmetric, or the sample size is fairly large, greater than 20 we'll say, and the data are not heavily skewed. Using the sample mean and standard deviation we saw in our sample, we calculate a 95% confidence interval for the mean mercury concentration in all Florida lakes. We find that interval in this case goes from 0.43 to 0.62. We could also use the t-test command in R to obtain a confidence interval. We see the interval matches what we calculated. Therefore, we are 95% confident that the mean mercury concentration level in all Florida lakes is between 0.43 and 0.62 parts per million. It's important to note that this confidence interval is describing the mean mercury concentration in all Florida lakes, not the mercury concentration in any single lake. It would be incorrect to say that we believe the mean mercury concentration, it would be incorrect to say that we believe the mercury concentration in any single lake is in this range, only that the average or mean mercury concentration in all Florida lakes lies within this range. Note that because 0.5 is in the interval, it's plausible that the mean mercury concentration level for all Florida lakes could be 0.5, and that's consistent with our previous result when we failed to reject the null hypothesis that that mean mercury concentration level was 0.5. In this video, we've talked about how to explain why it is necessary to include margin of error when using a sample statistic to estimate a population parameter. We've talked about how to determine whether to use a confidence interval involving mu or x bar in a quantitative situation, or a confidence interval for pi using p hat in a categorical situation. We haven't really talked about explaining how sample size and confidence level impact the width of a confidence interval, so I don't really expect you to be able to do that right now, although you might think about it, and we'll discuss it more in class. You should be able to interpret our output related to confidence intervals and write a sentence interpreting a confidence interval, explain the relationship between confidence intervals and hypothesis tests, and determine from a confidence interval whether or not a null hypothesis would be rejected. And finally, you should be able to determine whether or not it is appropriate to use a normal or t-distribution to construct confidence intervals.